welcome to this year's Project Lead the Way Engineering Design Development Capstone Course presentation. So we're glad that everyone could be here and have a chance to kind of show off the hard work from the students this year. My name's Michael Joy, and I'm the teacher for the course. I wanted to thank a couple people, specifically the jury members who are viewing the presentations live stream will be providing some feedback to the students on the work that they've done. So that's made up of some TVSD alumni and just local experts and professionals that have agreed to provide some feedback to them. So I really appreciate them doing that. Also to the school board and our administration team here at Twin Valley for giving the opportunity to the students for this course. It's really unique, and if you haven't been to these presentations before, I think you're really going to be impressed. Lastly, my colleagues for their help and really, throughout the whole school in helping get the students ready to this point. And they haven't had a whole lot of time to work on this when you think about it. So I've had them in class for approximately 110 hours this semester. So if you break that down, it's really less than 3 40-hour work weeks. Okay, so to go through this whole process, I think you'll be impressed with what they've done. So this is really just a small portion of all the work they've done over the last 4 years. So with that being said, I'm going to turn it over to them. Thank you.
Okay. On behalf of the students, we thank you for coming to our Project Lead the Way capstone course, Engineering Design and Development. This class is a cumulative course of all the courses here at Twin Valley, where we have 1 semester to learn and work through the design process. So each presentation is going to be about 25 minutes long, and we would really appreciate if our jury would complete 1 evaluation for each group. All right, so we are JKC, and this is our automotive assistive device. This is our final product before we get started. And you can also see it up here on the stage. So I'm gonna.
All right. I'm Leah Carwick. I'm a high school senior. I'm the president of NHS, the secretary of TSA, and a member of the Twin Valley mountain biking team.
And I'm Justin Bolt. I am also a senior, member of Stage Crew, Ski Club, and the Twin Valley mountain biking team.
My name is Caroline Brennick. I'm the president of the Twin Valley Design Club and a member of Stage Crew. So our objectives this semester. So we all had some form of connection to someone in the disabled or 65 and older group. So we decided throughout the beginning of the semester that we wanted to focus solely on helping those people and making their lives easier. So our problem statement that we came up with is, many Americans aged 65 and older are injured when entering or exiting their vehicles. This risk often forces them to resort to nursing homes or assisted living, decreased quality of life and autonomy.
All right. So one of the early stages is justification, and in order to know more about our problem statement, we decided to research some professional articles. A lot of them deal with rheumatoid arthritis, which greatly affects mobility when entering or exiting vehicles. So we wanted to mainly focus on disabilities or mobility issues so that our step can help more people.
To justify this within our local context, we did a community survey, which we sent out to a few healthcare providers, specifically nursing homes and nursing home residents. So we were trying to identify our target demographic through this. So we said, have you personally witnessed or experienced difficulty when entering or exiting vehicles as a result of motor issues, aging, or another disability? And 55.9% of our key people said, yes, they have experienced or witnessed that. So that was definitely a pertinent issue for them. Another one was asking them to rank their priorities when caring for or living with a senior citizen. And up first were quality of life and physical safety, so we knew that we were in the right ballpark trying to make it safer for people to enter and exit an automobile. Our last main question was, in your home or work environment, what is the approximate annual cost of mobility aids per senior? We were trying to get a ballpark and see what type of device people would be willing to purchase, and would this disrupt their day-to-day budgeting? We researched some analogous products, both products on the market and patents that were in existence, and we found a few recurring concepts as well as a few points of differentiation that we would have to decide on. So we found ease of use, integration, and intuitive setup to be recurring concepts, and some of the differentiations were the expected user mobility and the installation or the decision to have small repeated activations of the product.
So after we found all of these patents or solutions, we put them all into a similar solution matrix, and we came up with specification questions on the left side of what an ideal prototype would look like for us. And then we individually graded each one 1 through 5 for all the patents and solutions, averaged them, and got the sums for all of them, just so we can see what existing product or patent is closest to what we see as our design.
All right, so next we had to figure out if what we wanted to incorporate into our projects, like what ideas. So we started with a general idea, such as a standalone feature, so something that was outside of the vehicle. So we had ideas such as walkers, steps, things coming out of your car seat, and then our next mind map was related to things that were integrated into a vehicle. So things that would involve like moving your steering wheel or something built into the seat. Some of our early concepts looked like a walker with elevated ridge grips to prevent slipping, joints for easier storage and closage, and adjustable legs so that it could be integrated for each user. Our second concept was an arm that would attach to the back of your chair and was able to be moved so that it could be adjusted for the user's needs. And then our third concept was a set of stairs that would fold into the car with a grippy material to prevent slipping, joints for rotation, supports, and legs that would also be able to be heightened and lowered.
So after we came up with these 3 early concepts, we put them back into the decision matrix with the same specifications, and once again, we all individually graded them, and we found that the step scored the highest out of all of our specifications, so we decided to continue with that and use that as like a gateway to build the prototype, basically.
Upon learning this, we did a few market calculations to make sure that our target demographic was actually something that was significant and it would be relevant to our community and globally. So because 16.5% of the US population is 65 or older, the total available market within the US is 46 million older adults, and we deemed that to be a pretty sizable portion, so we were happy with that. Our expert contacts were people who helped us through the design process and just really made every idea very valuable just by providing us a little bit of that nudge and that feedback. So we had Jeff Biesfeld from Union Design, Catherine Dougherty from Presses Engineering, and Chad Snyder from Route 3 Labs. For Jeff Biesfeld, his advice came in the form of mentioning stability. So it can be found in existing structures such as camera tripods and then modified for EDD use, sort of extrapolating that concept into our own design. And then his principle of design was that simplicity leads to intuitive use and that concepts only really have value in context. For Catherine Dougherty, she mentioned that versatility is key. The design should be adjustable to different user heights, and good ergonomic design works for both the 5th and 95th percentile in metrics such as height and weight. Chad Snyder said that concepts are everyone's once they're on the table, and that having ownership of a concept ultimately defeats the process of putting a concept out there to be modified, changed, rejected, or accepted. His principles of design were that stability is key and to be aware of risk factors.
All right, so conceptualization. So we started off with using an old walker from up in the roof, up in the lab, in Mr. Joy's room. We used old boxes to like generally grasp what height we wanted our step to be, and using the walker to decide like, do we want a handle, do we want you just to rely on the car door? And this ultimately gave us the idea that we wanted to use a handle. So then we took it out to my car and really tested it there and figured out, was this best for drivers, was this better for passengers, how much weight can be put on it, how much stability do we need? And then we went to the drawing board for figuring out how to open and close it, because we wanted our prototype to be able to be opened or closed automatically. So we started with the idea of using gears and motors, and we figured that that was too complex for what we needed. Then we talked about magnets and strings, and even a twisting mechanism. And we thought about what hinges we wanted to use to open the legs. Then we decided to rip apart an old suitcase to really decide what we wanted our handle to look like. And this was easier for our CAD working drawings later.
Then we laid out some design specifications based on our conceptualizations. So we said that number one, we wanted it to improve safety for 90% of users, be able to bear 200 pounds before failure, weigh no more than 25 pounds, and be easily handled by less dexterous hands. We also said that we wanted it to have a base smaller than 3 feet by 3 feet, able to be properly utilized by one person, be able to tolerate temperatures between 5 degrees Celsius and 30 degrees Celsius, be resistant to rust, and be less than $500. All of these were based upon our understandings of our target market and our audience that we got from that user survey. We wanted to make sure that our target audience, people with decreased mobility, would still be able to get use out of this item, especially in temperatures that can fluctuate in a garage, or if it would slide, we wanted to make sure that they would have a good grip on it. Our underlying principles of design were put forth by our expert mentors, such as consumer safety, versatility, and project longevity.
All right, so here is a final picture of the finished prototype, and the way we have it set apart from others is that the handle can extend, which is why we have extendable, unfoldable. The handle can go flat against the base, and automatic is the button. You just press down the button and the legs will flip out. So that's the automatic part that we have. So, CAD highlights. On the left, we have just the mechanism fully exploded with some CAD notes, and then on the right, we have the entire mechanism fully exploded. There's a lot of triangles. So here is the assembly of one of our legs. The bottom piece is 3D printed, and then we sprayed that with Flex Seal later, and then the hinge, that's all we needed for it to attach to the base. Here we have the rubber mat. We found a rubber mat on Amazon and just cut out some circles and then just put it on top so that we wouldn't be standing on bare metal because that gets slippery. This is the top piece that we cut out with the plasma CNC in Mr. Joy's room. And these are the side pieces that we also cut out flat in Mr. Joy's room, and then, as you'll see later, we will bend them into place. And finally, this is the leg that we just cut out of some aluminum tubing. All right. So for 3D modeling, this is the first thing that we actually built technically, because we wanted to see what our prototype would look like in a 3D design, because up to this, everything was on CAD. We had nothing like built or planned or anything like that. And 3D printing is a great way of doing it because it doesn't take a lot of time, and you can see whether or not you need to make any changes, because having something in 3D, it just is a lot different than having something in 2D. You can actually like hold on to it and look around it and look at all the angles instead of just a flat piece of paper on a computer. All right.
Next came our resource allocation step. So we wanted to make sure that we had laid out our material plan before we went about purchasing anything to avoid redundancies. So we got our rubber mat and our legs and other materials. We had their vendors written down, and we tallied a total cost. And we made sure that we wrote any notes, such as it can accommodate more than one piece mat if we wanted to make any last-minute changes in the design, and just to be flexible. So we had our latch, our handle, our U-bolt, and then we had a total cost, and it came out to be $132, but some of that doesn't include things that were given pro bono by the school, so the actual cost was lower for our class. Then we had tools and equipment, such as our general welding apparatus and our roller bending apparatus, and we wanted to make sure that we had everything that we needed to manipulate our materials to make what we wanted. For equipment operation, all of our team members who were operating those devices had to pass the corresponding safety quizzes, and any other information that we needed surrounding the equipment came from Mr. Joy or a relevant expert.
So then came the really exciting part. We actually got to work in the lab and create our prototype. So first we started with the handle, which we got from a hand truck we bought from Lowe's. And we thought it was going to be more complicated, but it was actually just 2 bolts we had to undo. And then there's us lining it up on our physical prototype. Then we needed to create our 3D printing components, which we adjusted to the correct sizes, and then covered with Flex Seal to make them less slippery. So we covered the feet of the legs and our button. Then we got to use the CNC plasma cutter, which was a new piece of equipment for me, so it was really exciting and fun to learn something new. So here's a video of us using it. We are cutting out the top piece in this picture. So there's another picture of the final cut piece in Leah in front of the software. Then after cutting out the side pieces, the top pieces, and the mechanism piece, we had to deburr and finish them. So there on the left is me using a saw, can't think of the word, but, and then using a hammer to chip off some of the splat. Then came the bending process. So after they were finished and burred, I used a rolling apparatus to create a slight bend in them, but it wasn't quite tight enough, so I ended up having to use a hammer and some other outside forces to get that curve just a bit tighter.
All right, after that, we move on to the welding process. So before anything, I had to pass the safety test, as we did with any equipment in Mr. Joy's room. So after passing the safety test and after I got some guidance from Mr. Joy, I just did little spot welds all the way around, and they were strong enough to hold the, video. There we go. This is just an example. And I just did that all the way around, and then after that, I went to the angle grinder, and here's another video. I just went around the edges, smoothing all of them down from my mistakes. But, come on. There we go.
After that, we transitioned to cutting the legs. So you can see Justin here using the horizontal bandsaw to make the initial cuts. And then later what I did, because we found that we needed notches in order to have them properly seated on those latches that would release, I used the mill, actually, and I measured out individual cuts. And I had to make a few more cuts than we initially thought, just to make that seating just snug enough so that it would release very quickly for user ease. And then here's me. I'm actually notching out a piece of scrap wood to stabilize it, just because of the way that we had to set up the clamping. I wanted to make sure that everything had something underneath it, so that if anything went through, I would actually not be damaging the table. Cool. And then here's me cutting out the rubber mat just with an X-Acto knife. You can't quite see it, but I promise there's some cardboard under there. I did not cut up Mr. Joy's tables.
All right, so then came the quite tricky part, which was testing and figuring out the mechanism that we had spent so long drawing, if it was actually going to work. So on the left, you can see us. We had just got all of our components ready. Everything was cut out, and we finally decided to lay everything out and just see if it was going to fit. And then we attached everything to a wooden board just to see if pulling the latch would actually let the leg fly up and open. So there were a couple modifications that we had to make. We had to change out the springs inside of the latches because they were too tight for the button to pull them. So, and then there's another view of us testing. So creating the mechanism, we had to cut our nice fresh pieces right off the CNC into Swiss cheese, so it was a little scary, but we then cut pieces of the latches off to make everything fit properly. We also drilled holes in the latches so that we could thread cord through it to pull them open. There's us putting everything in once it's bolted. We were adding the strings, and then we had to add the rubber mat on top. So I used a hole punch to punch some holes in it, and I put dots of paint on each bolt that needed a hole cut around it, and I pressed it down, and it marked exactly where I needed everything to be. And then I angle grinded down some bolts, and then it was ready.
All right, testing procedures. So, with our criteria on the left already, we wanted to make sure everything was quantitative or qualitative and had a rough degree of accuracy. It wasn't going to be perfect, but we wanted to make sure it was relatively close. So, withstanding 200 pounds, weigh no more than 25 pounds, withstand temperatures 5 degrees Celsius to 30 degrees Celsius, and then we have, must be able to be set up by one moderately able-bodied person, handle easily operable, the handle is easily operable by 90% of users, and then assessed by at least 80% of test users to be helpful. Okay, so it successfully carried 200 pounds, or one of me, so that was an easy test to get done, out of the way. And here's a little video of one of the legs flipping out for the first time. There you go. And then that That was just the same for all of the other 3 as in this video. This is all 3 of the legs flipping out at roughly the same time, but that is the automatic part that I referenced earlier. And test. This is the first full setup of the finalized prototype in the hallway. So the handle extends and it folds flat, and then you press the button, all legs go out, boom. Took like 5-10 seconds, not even. This thing is really annoying. Okay, as you.
After our prototype was fully completed, we found that we wanted to make some modifications, mostly for user safety, but also just for ease of use. So the first modifications that we made were, we had these little 3D printed feet on our legs, and it turns out that PLA filament is actually pretty slippery when you put it on concrete. So the first thing we did was applied some rubber sealant, Flex Seal, so that that wouldn't slip as easily, so that we would have a better surface contact. We also did that for our button because who knows what's on everybody's feet. We just wanted to make sure. The other modification we already mentioned, we shortened those springs so that it would have a lower spring constant, so we would have less pressure on that, so it would be easy to release. And then one of our concepts that didn't even make it into the final prototype was the chamber, where we actually had horizontal and then vertical motion of our thread. And instead of doing that, we made sure that the thread was initially only horizontal so that we didn't have to go through translating the motion and translating it back, because there's all sorts of points of failure, and the fewer you have, the better off you are. And then future changes, if we could continue the project, one of the things that we'd like to see is having one bar across both of the hinge latches that you use to sort of put the handle down, because we think that would increase user ease. Instead of having somebody with limited mobility touch both of them at the same time, one bar would be way easier mechanically.
Okay, and then some of the closing thoughts that we had. So to analyze this course from an outside perspective, it gave us a successful carrying capacity. The mechanism we figured out was overly complicated, but we did have successful deployment in the end. Some engineering concepts that we learned were that ideas belong to the team, not an individual. The simplest solutions may be the most valuable, and the first solution is rarely the best solution. Throughout this semester, we had some amazing mentors, classmates, and experts to assist us with our project. A few names to mention. Mr. Joy, we thank you for your patience and assistance, for waking up early and staying after school late, gold star stickers, and making us laugh, even coming in injured. We appreciate you. To our fellow classmates, we enjoyed going on this journey with you and helping each other become better. And to our experts, we thank you for teaching us new concepts and how to think as real engineers. We appreciate your support in helping us through this process. Thank you.
Hello, my name's Katie Sharp, and we are Rolling Industries, and today we will be telling you about our beach mat receiver. So as I said earlier, my name's Katie Sharp. I'm in NHS Student Council. I'm the fundraising chair of Tri-M and the secretary of orchestra. I'm also the treasurer of TSA, and I run track, and I was the captain of the cross-country team, and in college I'd like to major in aerospace or in mechanical engineering.
I'm Dustin Rubican. I'm going to college for chemical engineering. Here at Twin Valley, I've been in the STEM-related courses about 6 times, and I'm currently a part of our TSA Technology Student Association. I've been in it for 3 years, and this year I am vice president.
I'm Emma Patton. I'm in NHS, and I'm a part of the volleyball team. I'm going to Lehigh University for mechanical engineering.
So our device is the beach mat receiver. It is designed to assist wheelchair users at the beach by acquiring the mat in which the wheelchair rolls on. And the way this works is the mat rolls around the axle of the device because the axle rolls with the wheels.
To choose our topic, we started with 300 problems and eventually narrowed it down to 10. We then used our decision matrix to narrow that down to our top 3, which were hail damages car windows, beaches are not wheelchair accessible, and hot steering wheel. We then talked it out for a couple of days and settled on beaches are not wheelchair accessible. This is our problem statement, which is 2.7 million Americans are wheelchair users and can find it hard to access the beach due to the limited amount of beach-accessible wheelchairs there are. The picture on the left is an existing solution, which is called the mobility mat, and the one on the right is a beach wheelchair. So some connections is my great-grandmother Patton. She was a wheelchair user for most of her life, and it was very hard for her to move, and she had little to no independence. For our problem justification, there was a complaint in Jacksonville, Florida, stating that there is a lack of beach wheelchairs and the ones that were there were too heavy. The picture on the left is the detailed complaints, and the one on the right is the federal response to the complaint.
In order to get a better idea of what prototype would fix the solution, we sent out a survey, and the two most prominent questions were: one, do you feel the need to have a personal beach chair? And 79.3% of surveyors said yes, 13.8% said no, and 6.9% responded with other and wrote in their own answer. And all those answers revolved around not going to the beach enough to justify spending an absurd amount of money on one. There wasn't enough availability of these devices, and the cost was too great. The second question we asked was, what's the range of money you would be willing to spend on a personal device? 86.2% said $0 to $1,500, 3.5% said $4,000 to $10,000, and 10.3% said $1,500 to $4,000. So we realized we needed to get a device within the price range of $0 to $1,500.
With our survey results in mind, we then researched existing solutions and patents for solutions to be created. And what we found out is many of the solutions actually only equaled the comfortability of the wheelchair, motorizing the wheelchair, or using a mat. But however, all of these solutions to be made would not allow the wheelchair user to change direction at their own discretion. And then on this next slide is just an example of what the battery-powered or motorized-powered wheelchair would have looked like. It would have had the battery stationed on the side with 2 thick tires.
So on top of researching patents, we looked at the existing market, and one of the options we found were the mobility mats. And these, while they are great and they are the cheaper the two options we will be showing you, they often limit wheelchair users' paths, and as you can see on the screen, it's a up and down path, and they can't really move around the beach. Also, these don't solve the issue of the wheelchair users not being able to move on the sand, and these are not on all beaches. The second solution is the Action Track, which is a motorized all-terrain wheelchair that is very comfortable according to its description. However, there are many cons with it. For starters, this is an extremely heavy device. It weighs 450 pounds, so it's very hard to transport. The other major con is it's $17,500, which is an absurd amount of money, and the average American cannot afford this.
So after researching our existing solutions and patents, we started brainstorming. This is our first mind map. These are 2 close-ups of our mind map with the cart idea, which included fat tires, ramp, a joystick that would be connected to batteries, so it would be powered, and clamps that would clamp down the wheelchair, which would be on top of it. And this is our second mind map, which focused more on attachments on the wheelchair. And this is close-ups of concepts 3 and 4, which are the spring wheel and the tri-wheel. And then these are some personal brainstorms that we used to create our mind maps. So the first 2 design concepts is the one on the left. That is the puzzle pieces, which that was based on more of where the user wanted to go. And the second one is the cart, which based on more independency.
2 more design concepts are shown. On the left is a wheelchair attachment kit, which uses 2 thick tires on the sides that are controlled with a lever or latch system. And how it works is there would be 2 thick tires on the very outside of the wheelchair that as you flick the lever down, they would release to the ground and lift you up, which would then be used in rough terrain at beaches or so. And then if you unlatch the lever, raising the tires back up, then you would have your standard wheelchair tires, which could be used on streets. On the right, you can see a spring wheel design, and how that worked is it would have been a rubber tubing as wide as thick tires are used at the beach with spring contraptions on the inside that would adjust to the form of the existing wheels on the wheelchair.
So as we went to decide which of our design concepts we would turn into a prototype, we looked back at our initial goals, which were 1, to lower the cost and create a cost-efficient device for users. Two was to allow independence for the user, which was a glaring issue we found with many of the devices. 3 was to make it have personal ownership, so an average American can own it, which goes along with the personal ownership. The next was to make it storable, so when someone does own it, it's not a burden in their house. And also we wanted to create a safe device. Then after we went back to our initial goals, we put all our 4 solutions in a decision matrix and had our specifications on the left, and we ranked them with weight, and then we ranked how much each concept met that goal. For instance, if it was independent, it was either ranked a 0 if it wasn't, or 1 if it's not. And the mats got second, the mats got first, the spring wheels got second, the tri-wheels got third, and the cart got fourth.
When creating our design concepts, after we finished, we contacted some experts. The first expert is Nate Siegel, who is a professor for mechanical engineering at Bucknell University. He liked our motorized cart concept the best. Then Nick Roscoe, who works at Lockheed Martin in space systems. He liked the puzzle piece mat concept the best. Then through our construction, towards the end of it, we contacted Thomas Legal, who's a mechanical engineer and a former EDD student, so he knew a lot about what we were going through, what process we were going through, and he made suggestions on attaching the cart to the wheelchair. And this is our Gantt chart, which helped us manage time and to stay on track.
After consulting with our experts, we then went to creating sketches of our model. After we used our sketches, we then went to Autodesk Inventor, which is a program where we created a 3D model of our device. On the right, you can see the assembly view of the device, and on the very front of it are the 2 attachment bars that are on the back of the wheelchair, the main framing and the tires. And then on the left is an explosion view that shows how it is assembled together. This is an up-close of the assembly view, and as you can see, it has the plate on the very left at that top left corner on the wheel, which allows the axle to move with it, along with the main assembly and the bearings. The explosion view shows that it is held together with screws and bolts to keep the pillow block bearings in place, along as the tires in place from sliding on and off of the device. The main framing was attached together by being welded, which is not represented in here because you can't really represent that in the explosion view. And then the 2 front attachment bars are shown in the very front, which attach to the device with a rope. After we created our assemblies and explosion views, we then created working drawings, which assisted us in the construction phase of our device because they gave us the dimensions of each part that was created, along with construction notes on how to create each part.
So after we made it in Inventor, we created a 3D model of it. The wheels and the frame and the 2 front pieces are all 3D printed, and the axle is a wooden dowel rod we had in the classroom. So as we were doing the creating on Inventor, we also did a cost analysis to see how much this would cost in the real world, and we found it would roughly cost $289.62, so about $300, and that did go into our specification of being under $1,500. So as we got into the construction of the prototype, on the left, I am cutting down parts of the frame.
In the middle, I am drilling holes in the rim of the wheel. That way I can attach the disc, which will allow the axle to move with the wheel.
And on the right, I'm practicing welding to weld the frame together.
Over here on the left, I am measuring the height and width of a bar to make sure it matches the dimensions in the working drawings.
In the middle, I'm drilling holes in the sidebars of the frame. That way we can attach pillow block bearings to allow the main frame to move independently from the axle.
And on the right, I'm grinding down the small plate that is welded onto the attachment bar.
Over here on the left is a picture of the welded frame.
In the middle, as you can see, I'm wearing the welding gear. We learned safety in this process, and also this was a really cool experience for me because this is my first time welding, and I was a designated welder for my team.
The very right is just when we first created our device. It's the initial assembly that we had.
Here I'm practicing welding to then weld the frame together.
On the very left, after we had the assembly of the device, we then had to get the mat to width. That way it could fit within the two sidebars of the frame, and that's what you see on the very left.
And in the middle, Dustin and I are attaching the device to the wheelchair so we could then test it. And on the right, it's just a close-up of me attaching it.
On the very left is a close-up of the disc that attaches the rim of the wheel to the axle to allow the axle to move with it. And this was needed because the inside of the wheel had bearings that initially prevented the axle from moving. And a major part of our device was that we needed the axle to rotate.
In the middle is just a close-up of how the mat looks rolled up on the axle. And on the right is a close-up of how the attachment bar is attached to the bar that comes out of the wheelchair. We use 2 hose clamps.
After we finished constructing the device, we then went to testing, and one of our initial tests was to see if the mat would roll. Now, one issue we ran into with this was, as you can see in this video, this mat slides with the device, and that is because the axle compared to the wheel is not a 1-to-1 ratio, meaning that because the wheels are much larger, as they roll across, the mat isn't moving as much as the wheels are. We then tested if the person pushing the wheelchair could walk comfortably, and at the same time if they could walk on the mat. And although they can walk on the mat rolls up, it does get dragged along, as you can see, and also they didn't have a lot of room because the sidebars could have been cut a little longer. After that, we then tested the weight capacity, and all we needed our device to do was withstand the weight of the mat, which succeeded and did not create any deformations in the actual device. Some improvements that we could make when we ran these tests is we could make a wider axle in diameter, and this would get us a closer 1-to-1 ratio of the wheels to axle. We could use a smaller wheel, which would also get us closer to that ratio, and the longer sidebars could be used in order to give the person pushing the wheelchair more walking room. After we looked at our improvements, we then created a device which is a 3D printed cover for the axle, which acts as both the wheel and the device in which the mat rolls around, which has a good 1-to-1 ratio so it doesn't get pulled along further. And in this video you can also see that the device works with 2 mats. So once the first mat is rolled up, then the person pushing the wheelchair can detach it and roll it to the next way in which they want to roll it.
So what we learned. We learned time management, meeting deadlines, how to work together as a team, new power tool operations. We had to do a lot of safety quizzes to make sure we learned the correct way to perform the operations. We also learned flexibility and leadership.
Overall, we believe this device has a lot of potential to help fix the solution, especially with the improvements we have suggested and made. Solving the problem itself does have a lot of challenges. However, we do believe that everyone deserves to have access to the beach, so we would like to have this problem solved.
And lastly, we would like to thank Mr. Joy, Mr. Bowman, Miss Bowen, Nate Siegel, Nick Roscoe, Thomas Legal, and our peers.